Okay. Uh, Good afternoon, everyone. Am I audible?
Audible.
Okay. Let us wait for like 1 2 minutes, and maybe some other students will also join, and then we can start today's session. Good afternoon, everyone. Am I audible? And is the screen visible to everyone?
Yes, sir, it's audible and the screen is also visible.
Okay. Uh, just a minute. So, everyone, this is our fifth problem-solving session. I am Adnan Farooq Khan, and I'm doing my PhD from IIT Delhi. And today is the fifth session for problem solving for the course Design of the Power Electronic Converters, which is being taught by Professor Shabrin Nath from IIT Guwahati. Like every week, this session is from 3 to 5, 3 to 5 on every Sunday, and every other weekend. Today, I'll be first going through what has been taught in this week, and subsequently, uh, I shall be moving towards the problem solving part, which shall help you in this problem solving assignments that has been given to you. So coming to this week's summary, so what had been taught in this this week, last week we had seen like gate driver design and then snubbers and etc. In this week it was all about power losses in the devices, and due to that power losses, what we know is we have a rise in the temperature in the devices, and so on and so forth. And mm, then what was taught is about like the thermal modeling and how we are going to choose particular heat sink for a particular application and a particular power loss in order to limit the junction temperature for a particular device below the maximum temperature that has been provided in the data sheet, so that the device would not get damaged, and so on. So yeah, coming in for in the detail coming to the detail, what have been we no like we had seen that uh, previous weeks we had seen about the gate drivers and snubbers. Now moving towards the power loss component in our converters, there are mainly we know like there are mainly two main power losses. One are the semiconductor losses. These are the losses that are associated with the devices. As you can see here, uh, we have a semiconductor device here. Like for a bar converter, we have a switch here, MOSFET, and here diode. And what are the losses that are associated with these devices? These constitute for our semiconductor loss. And in our semiconductor losses, there will be mainly like two losses, a conduction loss, and other loss will be a switching loss. Conduction loss will be mainly during the conduction when our devices will be conducting, and there will be some current that will be flowing through the device. And we know ideally there shouldn't be any drop across the device in the ideal case, but as we know, in practical in non-ideal cases, in practical applications, there is some voltage drop across the device, and if we have some current that is flowing through the device at that moment, and that would cause loss in that devices. Also in some devices, like what is being provided is RDS on, like during the on state of the device, during the on state of the device, we have this the on RDS on is provided for the device, and if we know this are like and we know the current that is flowing through the device, and we can have the RMS of that current, and from that we can calculate the loss component in a particular device. That this was about the one of the losses that will be in that we have in our devices, which we shall go into the detail, like how it is being calculated uh, in the subsequent slides. The other loss that is in the devices are the switching losses, and we know like these losses are in the devices whenever like we turn on the device and turn off the devices, and at that moment we know like there is an overlap between the voltage and the current, because like we saw the turn on and turn off process in the previous sessions, and we saw there like during the turn on or turn off, like one of the like during the turn on, first the current rises and then voltage drops, and there is an overlap between the voltage and the current for some amount of the time during the turn on, and same goes for the turn off. And when during that period, then there is some loss that is associated with the devices, and that loss are like the switching losses, because like these losses are in our devices at that particular switching intervals. This was about the outline about the switching losses, and coming to the magnetic losses, as you can see, besides these switching devices, as you can see here, like there are other magnetic components like the inductors, and these inductors, like we have besides these inductors there will be some parasitic resistance associated with this resistance, with this inductance, and whenever like there is a current flowing through this magnetic component, there will be some loss associated with this as well. And besides this, as we know, like for to have some inductance, like we wound the coil on a uh, particular like on a particular like a core, which may be a ferrite or a sandest or some other core, and there will be some losses associated with the core, in the core as well, like because of the change in the flux, and so on and so forth, these losses are, and these losses come under the section of this magnetic losses associated with devices. And mainly like during this week, the whole focus was on the semiconductor losses, what we'll be going through this, and in the subsequent weeks, like about the magnetic losses will be taught by the respected respected uh, professor in the subsequent weeks. So yeah, so this was about the losses, and you know the conduction losses, as I told you earlier. These are the losses, like if we have some is my screen visible? Yeah, it's now. So I told you like there are devices in this. If this is the topology, if you can see here, of the buck converter, and like there are devices like the MOSFET. There will be, whenever this MOSFET is turned on, there is some current flowing through this IL during the DTS interval. This MOSFET is turned on and there is some current flowing through this, and ideally as I told you, ideally there shouldn't be any voltage across this device at the time of turn on, but there might be some voltage across this device, and there will be some current that will be flowing through this switch, that will be equal to IL for that DTS interval that is being shown in this graph here. So This is the if you can see here, if we assume this voltage to be constant, but you can see this current is not constant for this particular time interval. So what we do is we mainly calculate the average of the power loss in a particular switching interval. And you see here, like, the current is not constant and it is varying in a particular DTS interval. It varies in a particular DTS interval, and we know, like, if we still assume like the RDS or the voltage drop is constant for the time interval, but due to the variation in this current, there is a power loss also varies over this DTS interval. So what we do is we usually calculate the average of the power loss in this in a switching interval, which is nothing but the product of this, like the voltage at that interval and the current. And for the average power, what we can do is we divide it by the switching time interval from the 0 to t. We integrate it, like Vt voltage at that moment and the current, and we integrate this, and this will give us the average conduction power, and which will we see in the subsequent slides. So here, so if you can see here, the conduction, as I told earlier, like someone has written something. I think this is the question, like we can discuss it in towards the end. Like, this is the question, uh, I think the assignment problem for the previous week. This we can discuss at towards the end, how to like deal with this question. So coming towards this, so we can see it towards the end. So coming to this about the conduction loss, like I told you, for a particular in a switching interval, a particular device will be on for a particular time. Let us say here it is for the DTS interval, and it will be off for like 1 minus DTS interval. During the DTS interval, the switching voltage ideally should be 0, but there will be some switching voltage across it, and there will be some current that will be flowing through the device. It will be equal to IL, that is the inductor current, as we know in the buck converter. Will be the switching current that will be flowing in this interval, and will, as the MOSFET will turn off, the switching current will go to 0. At the start of the interval, whenever the switch turn on and turns on, there will be a switching loss associated with this, like a turn on switching loss. And at this point, at the end of the DTS interval, there will be a switching turn off switching loss associated with this at this point. And during this interval, there will be a conduction loss. And how to calculate this conduction loss, as we know, I told you earlier, like this conduction loss usually is since this is a varying over a time interval. What we do is we calculate the average of the power loss in a switching cycle. So that will be equal to like 1 by Ts integral of the V switching and I switching in this turn on time. As you can see, we do it integral of 0 to dts of V switching into I switching into dt, and divided by the total switching time interval, and that will give you the average of the power loss, conduction power loss during a switching cycle. But here we know that V switching will be equal to I switching into RDS on, because in the MOSFETs we are provided with the RDS on, and if you assume like the RDS on is constant, then V switching will be equal to I switching into RDS on. and if we substitute this V switching in the first equation, we'll get P conduction will be equal to I square switching into RDS on. And what this means is that we can, if we know the switching if we know the switching current and RDS on, we should be able to calculate the conduction power loss in a particular switching interval, and that will be given by 1 by Ts into 0 to dTs. And if we integrate this, and it will come out to be equal to, the conduction loss will come out to be equal to I switching RMS square into RDS on. So if we know the switching RMS current, RMS of the switching current, and we know the RDS on, like we can get the RDS on through the data sheet of the device that will be using for a particular topology. This P conduction loss can be calculated. So P conduction, as we see, like going into the further detail of this P conduction loss, as we know, P conduction loss will be equal to square of the RMS switch current into RDS on. And if we like calculate this RM switching current of the RMS of the switching current, it will come out to be equal to root of like D into IL square, where IL is the average of the inductor current in the steady state, plus delta IL square by 12. This delta IL is the peak to peak ripple uh, in our inductor current, and that will flow, because we know, switching interval I switching will be equal to inductor current whenever this is on. If you can see it here as well. And if we calculate like here you can see, if you calculate the inductor current RMS as well, like the inductor current that is flowing, it will come out to be IL square plus delta IL square by 12 here. So if you see the equation 2 and 3, you can see there is a similarity between these two equations. And what is that similarity? What we can deduce from the equation 2 and 3 is that I switching RMS will be equal to root of D, where D is the duty ratio. Duty ratio is the amount of the time like our device turns on for a particular time in a switching interval, times the IL RMS current, IL RMS. And if you can see here, the IL RMS, if we assume there is a negligible ripple in the inductor current, we can assume that IL delta IL to be equal to 0. Then what we can assume is like I switching RMS will be equal to root of D times IL current. This IL, that is the current, steady state current flowing through the inductor in the steady state, average of the inductor current. So in this way we can calculate the RMS conduction losses for a particular device. And if there are n number of devices, if there are n number of devices in the topology, so we'll calculate a device RMS of the device current, and then we will calculate, and we'll see the RDS on for the particular device, and we can calculate the conduction loss through every device, and then we can add up those overall total conduction losses through the devices. So after the like conduction loss, there is another loss that is associated with our devices, is the switching loss. So here you can see the waveforms at the switching time interval. What happens is we have gone through the turn on of the device in the previous weeks, and we have seen this as soon what happens during the turn off of the device, like when we give VGS voltage, and VGS voltage is beyond the threshold, first the device current rises to the peak, and after that what happens is like during the Miller clamp, the voltage comes out to like the voltage falls from the steady state value to the zero. So we had seen this in the previous weeks, and that is what is shown here. Like we see during the turn on of the device, that the current goes from the zero to the peak to the maximum value first, and after that interval, like the voltage that is being blocked by the device, so goes from the blocking voltage and gradually dips it to zero. You can see here during this interval, first interval, during the interval the current rises from zero to the peak value, and there is an overlap between the current and the voltage, and after this the current assumes the steady state value, and the voltage drops from the steady state to the zero value, and there is an overlap of this current and voltage in this interval as well. So what happens is, like there is the power loss associated with this device in this interval, that we say is the switching turn on switching loss for the devices. And if we like multiply this Vs into Is, what we'll be getting, we'll be getting the power loss, and it will have a shape of a triangle, if you can see, because like this is rising and this is constant, and if we multiply this, we will have a like a curve like this. And during this interval it will be like this, and you can see it's a shape of a triangle, and the area under this will give us the power loss, and you can see this is given by this equation as we had earlier seen. If we want to do the average of this average power loss in this interval, it will be given by 1 by Ts, 0 to Ts, be switching into I switching, and the power loss will be given if we are able to, like, what we have to do, we have to integrate this area under this triangle and divide it by the whole time switching time instant. So if we like we know the area under this triangle is half of base into altitude, like you can see here this will be equal to VSW into ISW divided by 2 into T on, where T on is the turn on interval time, which comprises of the two times, like we had rise time of the current TRI, and the fall time of the voltage TRI and TFV, and the sum of these two time instants give us the total time on for the device, that is here T on, and it will be half of base into base will be T on, this altitude will be Vs into ISW, that is this, and this is half of base into altitude, and we had to divide, and this is Fs is because of this 1 by Ts, and we for the average power loss we had to divide it by 1 by Ts, and we know 1 by Ts is equal to Fs. Then if we know the switching voltage and the voltage that is being blocked by the device, and we know the peak of the current, that can you please like turn off your mic, and if we know the current that is flowing through the device, peak of the current that is flowing through the device after the turn on, we should be able to like calculate the turn on loss by this equation. In a similar fashion, like at the turn off time, what will happen is, like the current will like go from the peak value to the zero, and voltage will rise from the zero to, yes, there is an overlap, and we will come up to the similar equation here. There is only one change, like instead of T on, we will be having a T off at that time, and these two equations will give us the power loss during the turn on and the turn off. I think someone says mic is turned on. Can you please like turn off your mic? So this is these two equations will give us the turn on and turn off losses uh, for a particular device. Now coming like towards like coming towards what we should take as the VSW and ISW here. Let us say for the buck converter here, we know during the turn on time DTS, our device is turned on, and the switch there is current flows through the switch, and it is equal to the IL current in this interval. And after that, like the switch turns on, there will be a voltage that will come across the device, the blocking voltage, and it is equal to the V in. So whenever the device will turn on, like during this interval the device is turned off, but at the time of the turn on, before the time of the turn on, this voltage is being blocked by the switch, that is the V in voltage in case of the buck converter. And if you see, in case of the boost converter, this voltage will be equal to V out. So what will be the switching voltage here? That will be this V in case of a buck converter. And what will be the I switching current here? You can see at the time of the turn on here, the current that will be going through the switch will be IL here. IL, that is the average of the inductor current, and that will be subtracted by the delta IL by 2, because this is the current that will be flowing through the lower point, like the minimum of this inductor current will be flowing through the device at that moment. So we have to take ISW at that time. And during the turn off time, what will be the current? Like the device will be turned on at this interval, and at this interval what will be the current? The current will be the peak of the current that will be flowing through this device here, that will be equal to IL plus delta IL by 2. So and the voltage will be same as V in, that will be blocked by the device during the turn on, during the turn off time. In this way, like we'll be able to know the value of the VSW and ISW. And if we know the switching interval, like this switching frequency is given to us, like then we will be knowing the TS value. And in the data sheets, like we are providing with the T on and T off time, and if we put the values here, we should be able to like calculate the switch turn on time, and in a similar fashion the turn off time as well. The idea here is, like, you should be able to identify what is the voltage across the device, and what is the current at that particular instant. If you are turning on, at the time of the turn on, what will be the current that will be flowing through the switch, and at the time of the turn off, what will be a current that was previously flowing through the switch, and at that current our device is being turned on. If you know that, if you know the switching frequency, then we can calculate these losses by these equations. After that, this was about the DC-DC converter. We will be having some converter topologies where these losses may vary from one switching cycle to other switching cycle. Like here you can see in case of a single phase inverter, like where we have a sine PWM modulation, and we'll be having a pulsating voltage at the output. V out will be like plus VDC or minus VDC, and the current through the output will be a sinusoidal current here. And if you can see, in a particular switching instant, the value of the current will be different at each end switch. Sometimes it may be positive and it may keep rising to in a particular instant, it may decrease, and in some interval it may be negative. Compared to the DC-DC current, we had a constant average value, and over that average value we had a switching ripple. And if we assume that switching ripple is 0, then our current was equal to the average of the current, like inductor current flowing through the device in case of the buck converter, as we see. So here to calculate this switching losses is a bit tedious. So what we do is we use different simulation tools like LT Spice, etc., where we can simulate the actual device, and there are we can actually, the device will have its own RDS on, and we can simulate the device, and we can calculate the overall switching losses in a particular device. Other way, what we can do is we can simplify this. We can have the assumption that the ripple in the current is very minimal, and we can assume that the current is sinusoidal. and then we can see what is the current that is being flowing in a particular what is the current in a particular switching interval, and then we can analytically calculate the switching losses in every particular in instant by having some software tools in the MATLAB and some other tool mathematical, but it is a bit tedious process for this these converters compared to the DC-DC converters. Also, we have to take into the account the modulation strategy here as well, and we know that the losses might change with the modulation strategy as well. As you can see in the top, there is a bipolar modulation, and in the bottom there is a unipolar modulation, and you can see the ripple in the output current in the two cases are different. In the bipolar modulation that is in the top, there is a I think someone's mic is on. Can everyone please check if their mics are closed? So you can see in the bipolar modulation, the ripple there is more ripple compared to the unipolar modulation. As such, like in a particular switching interval, the value of the current at an instant of the turn off or turn on may be different, and maybe more, and that will be correspond to the more switching loss compared to the unipolar, where you can see the value of the ripple in the current is smaller, and we can have a different switching loss in this as well. So the modulation strategy for a particular converter may also have an effect on the devices such as semiconductor switching losses that we have also to keep take into the account. So after calculating the power losses associated with the devices, then what we have to see how we will be able to eliminate, and because of that power losses there will be a temperature rise in the device, and if there is a and if the temperature rise in the device is more compared to the limit maximum limit that has been provided in the data sheet, that can damage our device. So what we have to do, we have to see of the means how we can eliminate this heat that is being generated at the junction of the device because of these power losses, so that our devices may not get damaged. And one thing is there what we do is we do the there are a number of thermal cooling methods there how there are a number of cooling methods that we have in order to eliminate this heat from the devices and keep the device temperature in check. We can use the different heat sinks, and we can mount our devices on the different heat sinks, which provide a medium for the transfer of the heat, and which can subsequently lower the device temperatures and keep the device temperatures in the check. And for the heat sinks, we have the different ways of the cooling. One is the natural cooling, like we have a heat sink there and we mount our devices, as you can see, and there is a natural process by which the cooling happens there. And in some cases where the losses are more and we need to keep the temperature in the check, what we go for is the forced air cooling, and we will be having the fans associated with the heat sinks, and which will blow the air uh, where the fans will blow the air, which can subsequently help us in cooling the device. And other way of Other way of cooling is the water cooling, where we'll be having like you can see here a heat sink, and in the heat sink will be built in the pipes, and through these pipes a coolant or the liquid will be forced to flow, which will extract the heat from the devices, and limiting the temperature hike in the devices, thereby preventing any damage to the devices. And usually this liquid sort of a cooling is used in high power uh, uh, high high power converters, where the losses are very high, and we have to limit the temperature rise due to these high losses in the devices. And for that, what we do is uh, we should be able to know for a particular configuration of the converter, what is the requirement of the heat sink, and what kind of a heat sink we want to use, and we have to use. And for that, what we do is we do a thermal modeling of the devices, and how it's done, that will go through in the subsequent slides. And here we'll first go through the important terms that I will be using for this thermal modeling. First is like thermal resistance. Like this is the thermal resistance of the device. If we have a device or the heat sink, in the devices, in the data sheet will be provided with these resistances, and this is nothing but the ratio of the difference is in the temperature change and the amount of the power loss. And this equation, you can see, is analogous to the electrical equation, where r theta is here is the thermal resistance, and delta T is analogous to the voltage gradient or the voltage difference, and P is like analogous to the current in the electrical circuitry. And you can see this r theta is dependent on, if r theta is equal to L divided by thermal coefficient, and this A, RL by A, that means this r theta is also dependent upon the geometry or shape size of the heat sink device, or of the device. The other term that is being used is the thermal capacitance. It is the capacity of the heat sink or the device to store the heat, and it is being given C theta. It is nothing but the capacity to store the heat, and it is given the watt second per Kelvin. And this R theta for this is the Kelvin per watt, or Celsius. It can be also given in the Celsius C per watt. The other important term is the thermal time constant. It is given by the product of this thermal resistance into the thermal capacitance. What it gives is for a particular power, how much time does this take device or the heatsink take for the change in the temperature. If we have to dissipate a certain amount of the power for a particular how much time this particular heatsink or the device will take for to show this variation in the temperature from one temperature to another temperature, to dissipate a particular amount of the power that is being given by this time constant T. So now coming towards this thermal circuit, and we know if we know the device, we know inside the device is the die, and at the die is the junction. At the junction there will be some temperature, and this junction, the temperature at this junction is determined by this Tj, that is the junction temperature. And what we have to do is we have to limit this junction temperature below the maximum value that has been given in the data sheet. And after that junction, there will be a casing of the device, and this casing will be mounted on the heat sink. And between this junction and the case, that is the temperature at the case. First we'll be going about the temperatures. First, this is the junction temperature, then comes out to be the Tc. It is similar to the potential that, like I told you, in the electrical. This Tc is the temperature at the case, and between this junction and the case there will be some resistance that will be given by R theta Jc, the junction to the case thermal resistance, and this resistance will determine the dissipation like of the power from this junction. The amount of the heat that will be generated due to the power loss, dissipation of that heat, will be determined by this R theta Jc. After this, like case temperature will be having the sink temperature, and similar to this will be having a resistance between this case to sink, and after that this sink will be having an ambient temperature, and there will be also some resistance between this sink and the ambient, that is the like sink to ambient, like this resistance of this sink, thermal resistance of the sink, and it will be giving into the in the data sheet of the data sheets of the heat sink. So if we know these things, like these are theta Jc and Cs, these may be provided in the data sheets, and this R theta Sa may be provided in the heatsink data sheet. And if we know this R thermal temperature coefficient resistances, and we know the power loss, we can calculate the temperature at different points, like at the junction, case, or sink. And usually the ambient temperature is around like 25 at the room temperature, but in some like converters which are in the enclosure, this ambient temperature may be higher, like a 50 degree or 75 degree or so on. So as told earlier, like this thermal circuit is analogous to the electrical circuit, where power dissipation is equal to the current source, and the temperature at different points are analogous to the voltage potential as in the electrical circuit. And this theta, R theta and C theta are nothing but analogous to the resistance and the capacitances in the thermal circuit, in the electrical circuitry. Now coming to the steady state thermal response, as we know, we had seen, let us take an example of the buck converter itself. We had seen that we had turn on and turn on off losses in a particular interval, and that interval is very small compared to the total switching interval. And in a particular switching interval, this turn on and turn off interval will be very small, and the loss associated in this will be in that particular time interval. That is why like this power has been shown as a train of pulses, because like it has been like as shown, if we have a Ts, this loss will be in this time only, and this power loss will be comprised of turn on as well as the turn off loss. So let us say if we have a, in a particular switching instance, we had a turn on, we had a power loss. So whenever the device is turned on or turned off, what will happen? Like if we had a particular junction temperature, the temperature of the junction will rise, and after that, like device this switching loss, then the device may turn off, and there won't be any switching loss then. And after that, the devices will be off, and there won't be loss associated with this device, and then this temperature may dip. And if you can see, if the time constant is very large compared to the switching time, we can see like we can assume this will assume a steady state where the change is very small in the temperature, and where we have an average value, or there will be a variation in the temperature. In this case, what we can have, we can assume this network as the steady state in this network as this, where we'll be having the temperature at the particular junctions, as we discussed earlier: junction temperature, case temperature, sink temperature, and ambient temperature. And there will be a resistance between this, like junction to case and case to sink and sink to ambience. And these will be given by the data sheets of the devices, and some will be like this. Between this resistance between this sink and the ambient will be given by the data sheet of the heat sink itself. And we'll be having a power that will be dissipated, that will be having as an analogous to as I had earlier told you, it is an analogous to a current source in the power circuit. And this power dissipated will be represented by a current source here. And if we know this power loss, we can calculate the temperature at any point in this circuit. And how will we do this? And we'll be having, we can do this. Let us say we want to see the temperature at this junction point, and we know the ambient temperature, and we know the power loss associated with this. So similar to this electrical equation, as I told you, like I is equal to V by R, where we had seen here I is equivalent to the power loss is equivalent to the I. So average of the device power loss will be equal to, like this is the voltage between this the temperature difference between junction and the ambient is similar to a voltage. And we can have a resistance, and which are like these resistance between junction case sink and sink to ambient are similar to the electrical resistance. And this equation, if we know the power, if we know these resistance, if we know the ambient temperature, we can calculate the junction at any time. Or in a way, if we want to limit the junction temperature at any point, and we know the ambient temperature, let us say 25°, and we want to limit, let us say, junction temperature to a particular temperature, let us say 100° or 80°, or so on and so forth, we know the power loss, and we know this JC and CS through the data sheet. And we want to like now decide for the heat sink, what kind of the heat sink we want to use, and what should be the thermal resistance of that heat sink, in order that we to achieve a particular temperature at the junction. And that will be given by this R theta SA will be given to Tj minus Ta divided by Pd minus these resistance. And all of these values are known to, if all of these values are known to us, then we should be able to calculate the thermal resistance of the heat sink. And then we can look for a particular heat sink with that thermal resistance, in order to like how that is done, like we shall go through the questions and come up and you will see how we choose that heat sink for a particular device. This was about the thermal response in case where we had like time constant was very high compared to the switching instant. Now for another instant where we have is time like the switching in time is very high compared to the time constant, thermal time constant. In that case, what will happen, like for a particular power loss, there will be a large variation in the temperature, and the temperature may rise from one temperature to another, and the variation between these two temperatures will be very high. And in that case, what is being done is it is being the losses in that case are converted by these two methods. One is by this network, is called core network, the top one, where we have a, if we know the power dissipated, then we have this different values of like our thermal resistance and thermal capacitance, which will be provided by the manufacturer, and it will be form sort of a like a ladder network. And if we know the value of these resistance and capacitance, and then we should be able to like know the junction temperature and the case temperature in that case. in this fashion. Other way to do is using a Foster network. In this case, we have a series of the parallel networks of this R and C's, if you can see. And in this also, like, the values of this through the experimentation are being provided by the manufacturer in their data sheets for these networks. And if we know the power losses across these devices, and we uh, then we should be able to calculate the different temperatures. And for also we should be able to, in case for the design of the heatsink, we should be able to, like, calculate the thermal resistance of the heatsink and choose the proper heatsink for the device, for the converter. So coming to this, for this network, if you can see here, the other way, this is the, like, the part number IRG7PH42UDPBF, part number of the MOSFET. And for this MOSFET, like, there is, like, this graph that is being provided. And also you can see here there is a core network that is being provided, and the values of this R1, R2, like, these time constant are being provided, Ri and Ti are provided. And from this, like, we can calculate this the temperature at different junctions, uh, at different points, as we have seen. But the other way to do is, like, we can do it through the graphs using the this equation. Like, temperature at the junction will be given by Z theta jc, and we know the power average of the power dissipated through the devices, and plus Tc. If we know the temperature at the case, then we should be able to calculate the junction temperature. And how? Now the only thing unknown here is the, like, Z theta jc. And you can see here Z theta jc for the particular, there are a number of graphs provided for this Z theta jc. Like, if you can see the bottom one, this is for the single pulse thermal response. Where what is this single pulse thermal response? Like, we had a power loss one pulse, then after that there is no power loss, we had only the one pulse. So in that case, what is, like, let us take, we have a pulse duration of 10 micro, that is 1 e minus 5. So what will be the loss Z THJC at that point? So if you can follow this graph, follow the cursor, like you can see, we might have it will be equal to around, like, uh, you can see what is the value. Like, this is point between the 0.001 and, like, 10 milli. This will be around, like, 30 milli here at if we have a pulse duration of this 10 microsecond. So what is done, if for, like, if we are having a multiple pulses, and the duty ratio, and if we know the duty ratio of that pulse, like, let us say we have the power loss, and we know the duty, and that duty will be given by the TP, that is the time for which there is a power loss, and the total switching time, total time interval. And if we know the duty, and this may change from, like, if the duty is 0.01 to, let us say, duty is 0.05, the value of this Z theta jc will change accordingly. And if you know the duration of the pulse, you can calculate this Z theta jc at any point of the time. And if you know the value of the Z theta jc, you can put that value here, and you know the amount of the power to be dissipated, amount of the power dissipated. And if you know the case temperature here, then we can calculate this junction temperature. This is in the case of, like, where we have switching time greater than this time interval of this thermal network. This was about the graph. So now coming to this, if we want to calculate, like I earlier discussed, now we want to design the heat sink, select the heat sink for a particular topology. So what are the steps that we should follow? What we should have to do is we have to calculate the power, average power dissipated first, and that will be analogous to the current flowing through this uh, electrical circuit. And after that, the second step is we have to use the data sheet to find different thermal resistance, like junction to case. And there will be sometimes what is this case to sink is also provided in the data sheet, and if not, then we have to see what is the material between this case to the sink, this heat sink, and we can have to see the date from that particular material data sheet, see this uh, thermal resistance of that material. And what we have to also see in the data sheet, what is the maximum junction temperature we can go to, and we have to limit this temperature below that thing. And also what we have to do is we have to find the TA, ambient temperature for a particular application, what is the maximum ambient temperature we can go up to, what we want to limit it to. For if our converter is in the cases, what is the ambient temperature. And with respect to that, and if we want to also limit the junction temperature at a particular like uh, temperature, then these things are known to us. We can then choose a particular uh, we can then calculate this uh, the resistance between this thermal resistance of the heat sink. And if we know the thermal resistance of this heat sink, then we can choose a particular thermal heat sink with that thermal resistance. And what we have to keep into the mind, that the resistance of the thermal resistance of the heat sink should be the equal to or lower than the actually calculated value. Because the lower the thermal resistance, this means that it can very well eliminate the heat, and thereby lowering the temp and keep the temperature in check. So the formula to, as I told earlier, to calculate this R theta, if we know the junction temperature, know the ambient temperature, know this power loss, and know this junction to case resistance and case to sink resistance, then we should be able to determine this heat sink thermal resistance for the heat sink. And if we know this thermal resistance of heat sink, that we shall choose appropriately a particular heat sink for our application. So this was about what had been taught in this. Now we will go towards the problem solving session, and you will know how this thing is done. So this is the first question, and before that, we shall take a break for 5 minutes, and then we can start solving these questions after 5 minutes. So let us come to the first question. So what is being asked here is we have to design a buck converter using the MOSFET, and the part number of the MOSFET is also provided. And following can be noted for the converter, like there are the certain design specifications that are also provided for the converter, like that the input voltage is given, that is like 35 volts, and the output voltage is 21 volts, and the switching frequency is 50 kilohertz, and the ambient temperature is given to be around like 55 centigrade, and the average inductor current is IL is 6 amps. And also what is being assumed here is the switch current is equal to the average inductor current, and the assumption taken here into the consideration is that the ripple uh, we had the ripple has been neglected. The ripple has been neglected. So we can say here the first question that is being asked is calculate the typical turn on time of the MOSFET and turn off time of the MOSFET. Like in the previous session as well, like we had seen, if you will see here, like in the switching waveforms for the MOSFET, like during the turn on and the turn off time, what we have is first is the turn on time, turn on delay time, and there will be them a rise time, yeah, time, and during the turn off interval there will be a turn off time, and there will be a fall time, and this we had discussed in the detail in the previous uh, sessions as well. So the turn on time will be equal to the TD on plus TR rise time, and the turn off time will be equal to TD of the turn off delay time and the fall time. So the typical turn on and turn off, like this is the data sheet, and you can see that turn on delay time, TD on rise time, and turn off delay time and fall time are provided here in the nanoseconds for a particular test conditions, and for some other conditions except this, like these value may vary in the practical application, but here we have to like uh, take with regards to this data sheet, and you can see here turn on time will be equal to TD on plus TR, that will be 86 plus 16, that will come out to be equal to 102 nanoseconds, and similar fashion T off will be equal to 70 plus 62, that will come around to 132 nanoseconds. The third question is we have to calculate the value of the on state resistance, RDS on. So this is the data sheet here. If you can look at this data sheet, there are a number of things that we had discussed, like drain source voltage and so on and so forth, and there's also what is provided is drain source on state resistance, that is RDS on, and it is given to be equal to 0.085 ohm, and that is 85 milliohm. So that is the answer to the question, but this 85 milliohm is for the particular like VGS and drain current, but if these parameters vary, like then this RDS on also varies, like there is also a graph that is being provided in the data sheet where you can see that the junction temperature will vary with the RDS on, like if let us say our junction temperature is like 100 degree, then our RDS on will be equal to 1.75 times the actual RDS on. So if the junction temperature is high, then our RDS on will change, and for that purpose, like our power loss across the device will change. As we know, like as I told you, like this RDS on is not constant and it may vary, and due to this the variation in the RDS on, the losses may vary as well. So the next thing that we have to calculate is maximum junction to case resistance, like R theta JC, and typical case to sink resistance, and maximum junction temperature. And as I told you, like these things will be provided into the data sheet. Yeah, you just have to like look for the data sheet. If you can see here, the maximum junction to ambient. Here what we have to see is maximum junction to case. Maximum junction to case is given like 0.65 Celsius per watt, degree Celsius per watt, and typical sink to resistance. Case to sink resistance, and also the case to sink is given is flat grease surface, and for that the typical value is 0.24 uh, degree centigrade per watt. So these are the answer to these questions. And also what we have to see is the maximum junction temperature. As you can see here, what is given here is the operation junction and storage temperature range varies from -55 to 150 degree. So the maximum temperature range will be equal, junction temperature will be equal to 150 degree. So the answer to these questions is like 0.65, 0.24 and 150 degree centigrade. So now what is being done is, now what we have to do is we have to like calculate the conduction loss, switching loss and the power losses. Like we had seen the equation for this power loss. We know that the conduction power loss will be is equal to IRMS switch current square into RDS on. But we had seen that RMS switch current is equal to root D times the IL average current, and if we square that, it will come out to be D into IL square into RDS on. And we know IL is given in the question itself, it is like 6 amps, and we know input and output voltage. From that we can calculate the D, and D will come out to be V out by V in, that is 0.6. We have like D equal to 0.6, IL is equal to 6 square, and RDS on we had seen earlier, RDS on we had seen earlier to be at around like 85 milliohm. So if we like put these value here, like our conduction losses will come out to be equal to 1.836 watt, and if we round off, it will be equal to 1.84 watt. This is how we calculate the conduction loss. Now coming to the switching loss, like we knew we have to, like for the switching loss, we have the turn on and turn off loss. We had like, we know V switching into I switching, and we had like turn, if we know the turn on and turn off time, and we know the frequency of this switching frequency, then we should be able to calculate. And in case of the buck converter, like the switching voltage will be equal to the input voltage, and that is around like 35 volt. And also the assumption given in the question itself is like we have to take the switching current equal to the average inductor current, that is equal to 6 amps. And we had calculated the turn on and turn off time in the previous question, and if we put that value here, we have like 35 into 6, 102 plus 132 nanoseconds. Can you please, Niranjan, can you please turn off your mic? Nanosecond into the switching frequency, that is around 50 kilohertz, divided by 2, that will come around to be 1.2285 watt. That is, if we round off, it will be equal to 1.23 watt. So the total loss, power loss, that was about the switching power loss. And if you want to calculate the total loss, that will be equal to conduction loss plus switching losses, that will be equal to PC, that will be equal to like 1.84 plus 1.23, that will come out to be equal to 3.07 watt. So now we know the different R thermal resistance, we know the power dissipated, we know the turn on and turn off time as well. So in the subsequent question, what is being asked, like we will see. Now we have to calculate the sink to ambient resistance, thermal resistance, and we know if we had seen this, we know that the power loss, we know R theta jc, and this also we know, we had calculated from the data sheet, and now we want to calculate this R theta sa. And you can see, as I told you, like you can assume this as similar to an analogous to the electrical network, where this is this power dissipated is as the current source, and these are our resistance, and we can calculate the potential. These temperatures are the like as the potential at different points. So like discussed before, that R theta S1 will be given by this equation, like it will be equal to Tj minus Ta divided by power loss minus this resistance. And we know that the maximum junction temperature is like 150 degree minus we have the ambient or we have to keep the ambient at like 55 degree centigrade. We know the power loss, that is 3.07 watt, and we know that R theta jc is like 0.65 and this is 0.34. And if we solve this, like R theta sa will come out to be 30 0.0546, and that we can like round off to be out 30.05 degree centigrade per watt. So we have to like choose the heat sink where which has the thermal resistance of like 30.05 degree centigrade per watt or below. We cannot choose above, because if we choose the heat sink with the resistance above this thing, that then the temperature at the junction may go beyond 150 and which may damage our device. So this is the answer to this question. Now coming to the last question, I think this is the last question of this. Select the most appropriate heat sink for the device if natural cooling is performed. So if the natural cooling is performed, so there are like a number of heat sink and their part numbers are also provided, and next to the part number are the thermal resistance of those heat sinks to be provided. And we had seen like we wanted the heat sink which had the thermal resistance equal to 30 or below that. So like I think you should be able to answer this question. So yeah, like C is the correct answer to this question, because if we want to like limit this temperature, ambient temperature at 55, and we want to limit the temperature at the junction at 150 degree, like then we have to have the heat sink with the R theta SA less than 30.05 degree centigrade per watt, and part C only satisfies this criteria. So the C is the answer to this question. So now what is in let the heat sink this 21736 CTE is used with forced air cooling. Now what is being provided with this heat sink? A fan is provided for the air cooling, and a fan of 200 LFM is used. At this, R theta SA of the heat sink comes down from, we can see here earlier it was around 55, now it comes down to 16 degree centigrade per watt. Now what we have to see is the rise in the temperature. What is the rise in the temperature? So as earlier I told you, like this is analogous to this uh, electrical circuit, and if we have an electrical, this power loss is like a current, and we have to calculate the potential at this junction. So potential at the junction is nothing like how we see is I into R, like the potential with respect to the ambient. So it will be equal to P loss into Rj theta plus this and this, and it will be plus this, because this is the already this ambient temperature will be at some potential. If we consider it as a potential, this we have already have an ambient temperature, and if we like substitute values here, and the junction temperature will come out to be equal to 106 degree, and that is way below the maximum limit, that is around 150 degrees centigrade. I think these are the questions for today's session. I think all of you would have gotten the understanding about how to calculate the losses and how to design a particular heat sink if we know the device losses in order to protect our devices from overheating and limiting our junction temperatures to the particular below the maximum of the temperature provided in the data sheets so that our devices are not damaged. Yeah, that was it for the today's session. That was for the today's session. And if any of you have the any questions, like Suresh, you want me to explain the switching losses again? So it was about. So you can see here, let us consider here, like we had seen for conduction loss, you got to understand. Now we will come to the switching loss. So we had seen during the turn on of the devices, what happens is first the current rises from 0 to the maximum value, and after that what this voltage goes from the maximum value to the 0. And if you can see in this interval, there is an overlap between the voltage and the current during the turn on process, and there will be a loss associated with this, and that will be given by Vs into Vsw into Isw, and that will come out to be as a triangular waveform, and the area under this curve will give us the average of the power that is being dissipated in this turn on time. In a similar fashion, we can do it for the turn off time as well, where current will first go down and then the voltage will rise, and in a similar fashion there will be a overlap here as well. So if you want to now calculate the average of the switching power loss, it will be equal to 1 by Ts and the area under this curve. So if you see, this can be assumed as a triangular curve, and we know the area of the triangle is half of base into altitude. So we have Vsw into Isw, and turn on time. Turn on time will be given by the rise time and the fall time. Rise time of the current and the fall time, sum of this, and divided by 2. This will be the area of this, and 1 by Ts, we can have this Ts equal to Fs. If we know the switching frequency, this will give us the turn on power loss. In a similar fashion, we can calculate the turn off power loss as well. Here only the difference is, instead of the turn on time, we have to see the turn off time during which our currents and voltages will overlap. I hope you understood about this turn on loss. If you have any other question, kindly ask. If there are not any other, if there are no any other question, if there are not any other questions, then we can conclude our session today. Thank you everyone. This was it for the today, and like these, what is this previous job? I'm not able to understand what you are asking. Suresh, can you please turn on your mic and ask what you are trying to say? Okay, CS and RS value. If you go through the material that has been provided with you, there was if you know the chi value and the zeta value, and then there was a particular equation that was given. If you go through the the problem solving session of the previous week, and also I had provided with the I had provided with these slides, there is a particular equation. If you go towards the later end of the questions, how to there was a particular value of chi and zeta provided, and how using a particular that equation you are able to calculate first the CS and the RS value. I hope like this will help you. And still, if you are not able to calculate, in the next problem session, like we can discuss the question in detail. That equation, like I don't have it in the back of my mind right now, but you can certainly, like in the previous Lee we had seen the derivation of that equation, and if you go through the lectures, previous week's lectures and transcripts, like that equation had been like derived in detail. Kindly go through that, and if you are not able to understand, then you can mail and or ask in the next problem solving session, and we can discuss that. You first please go through that and see, because everything is provided in there. Is that fine? Okay. Thank you everyone, and if there are not any other questions, then we can conclude for today. Okay. Today's like these presentation and this video will be recorded and it will be shared with you. Okay, thank you everyone. Okay, that was it for today, and thank you so much.